Okay, so this is a list of theorems about integrals and analytic functions. And first we need a big pile of definitions. Most of these are pretty straightforward. So a smooth path is, we've seen these, just a differentiable function, gamma from A to B to the complex plane. It's just a path. A smooth path is simple if it doesn't intersect itself, right? So it doesn't cross itself. Technically, that means that the function gamma is 1 to 1. The trace of a path is the image in the plane, right? So if we have a path that looks like this, what a path is a map from A to B in the real line. Oops. Oh, boink, boink. Supposed to put gamma over the arrow. And then this is in the complex plane somewhere. It's some kind of a curve. And so this shape here, the thing that looks like a lentil bean or something, that's a set in the plane. It's a subset of the plane, right? So it's two things. It's a subset of the plane, but also it's a function. It's the image of a function from the real line. So clues, we usually call gamma of A the start of the path, gamma of B is the end. I call it that. That's not standard terminology. So this is a closed loop where my start equals my end. A closed, simple, smooth path, which is what this is, right? So it's closed because it starts and ends at the same point. It doesn't cross itself, so it's simple. It's smooth because I've got a derivative, and it divides the plane into 3 parts. The exterior, which is out here, exterior of gamma. The interior of gamma, which is inside of it. And then trace of gamma, which is the path itself. A simple, closed, simple, smooth path has a direction because gamma of t has a derivative. So we've got a derivative vector. So I've got a direction that I'm traversing this thing in. If the interior is on your left as you go around the curve, it's positively oriented. If the interior is on the right, it's negatively oriented. So counterclockwise, right? The way you go around a unit circle, that's positively oriented. So that's the basic stuff we need to know about curves. So domains, open and connected set. Simply connected just means that every simple, closed, simple, smooth path whose trace is in D has got its interior is in D. So simply connected just means you have no holes. Right? So here's a set. If I pick a path, gamma, that lies inside of it, right? The entire inside of gamma is in that set. So that's simply connected. Multiply connected just means that I can draw some set. Here's my set D, but it's got some holes in it. So D is this set without the holes. And that means I can take a path, gamma, and now the interior of this circle, this closed path, its interior is not entirely within the set because there's a hole. So that means multiply connected. And what we'll see as we go forward is that holes will be connected to poles of the functions. So if you have a function like 1 over z minus 1, right, that's not defined with z equals 1, right? So its domain has got a hole in it. Some notation, nth derivative function is denoted by this, an n in parentheses in the exponent. And if gamma is a path and there exists some open set U, so the trace of gamma is in U and f of z is analytic on U, then f of z is analytic on gamma. So that just means that if I say here's a path, f analytic on gamma means actually that I can find a small open subset that goes around the path, right? And it's often referred to as a collar. So that f of z is analytic actually on this whole set that includes the path, okay? Because technically you can't, on a path, right, you can't define a derivative because you need the whole disk around each point to define a derivative, so they have the limit. So we need an open set. And finally, the following equivalent means that any statement in the list implies all the other statements in the list, TFAE. So this is, last time, the ML theorem was where we were. I think this is the last thing that was proven in the last set of notes. And that's just basically saying if I have a path, start to end, and have a function that's defined on that path, and it just has to be continuous, not analytic, and it's bounded, right? So if you think about this, this is not exactly a good picture of it, but if you think about the modulus of the function, right, with this height above the path is the modulus. This is saying that the modulus is bounded by something above, right? And so the integral of the path, the modulus of the integral along the path of the function, that's not what I wanted to do either. There we go. Integral around gamma of f of z dz is sort of what you think it would be, right? Under here, it's got to be less than this height times this distance, right? Length times height. And that's a pretty familiar thing from just algebra. You have a, not algebra, from calculus. You have a similar thing. So the last thing that we did in class was looking at this. So we have a domain and a function is continuous. And we want to know the following are equivalent. So what that means is, and this is what I call the Tfa theorem, the following equivalent. 1 implies 2, 2 implies 1, 1 implies 3, 3 implies 1, 2 implies 3, 3 implies 2. If any one of them is true, all 3 of them are true, right? And we sort of started working through this. You can do 1 implies 2 is if there's a function in the domain that is the antiderivative of little f of z, the path integral along, and I'm looking for my notes, there we go. Oh, how do I want to do this? I want to do this way. So if I have 2 paths, we'll say we're going from some start point to some end point, and I've got a path gamma 1, and I've got a path gamma 2, and everything is inside this set D. That's our domain. Then integral around gamma 1 of f of z dz is what? Well, this is just the basic definition of a contour integral. And so that is integral around gamma 1 of f of gamma of t times gamma prime of t dt. Right, so what we're doing here is we're setting z equal to gamma of t, dz equals gamma prime of t dt. It's just a straight up integral by substitution, but what's the derivative of this function? Oh, it's not along gamma. We've changed variables, so now we're going from a to b. The derivative of the antiderivative along the path is, well, this is the chain rule. So f prime of gamma of t times gamma prime of t. But this is the antiderivative of that, so this is f of gamma of t times gamma prime of t. So this integral now, and we'll push this down so I have more space. So my integral becomes integral around gamma 1 of f of z dz is equal to integral of d by dt f of gamma of t, but no, f prime of gamma of t times gamma prime of, oh, I confused myself. Sorry about that. I just want that. And the fundamental theorem of calculus just tells me that the derivative, the integral of a derivative of a function is just the function evaluated from where you end minus where you start. And that clearly doesn't depend on which gamma I choose, right? No matter what gamma I choose, that'll work. So the function, the antiderivative gives us that path integrals are independent. If path integrals are independent, then integrals along a closed smooth path will be equal to 0. So 2 implies 3. If gamma is a closed smooth path, right, what's that integral going to be? Integral around gamma of f of z dz. Well, I'll just pick some point on the path, call the path that goes to it this way sigma 1. Here's my start and end. Call the path that goes this way to it sigma 2. Then gamma is equal to sigma 1 minus sigma 2, because gamma is following sigma 1 and then going opposite sigma 2. So that's the integral along sigma 1 of f of z dz minus the integral along sigma 2 of f of z dz. But these are both paths that start here and end here. So these two integrals are equal, so that whole thing is 0. Pretty straightforward. And then 3 goes to 1 is just saying integral around gamma equals 0 on loops implies there is an antiderivative. And you define the antiderivative at some point z1 as being the integral along gamma of f of z dz, where gamma is a function from a to b, and gamma of a starts at some point z0 and ends at the point that you're interested in. So define a function by saying it's a path integral. Oop, that's not what I want. So in my domain D, I pick a point z0. If I pick any other point z1, I define a path, any path, from 0 to z1 and say, well, capital F of z is the integral of f from z0 to z1. So why is this path independent? Why does it not matter which gamma I choose? Well, it doesn't matter because we're 0 in loops, right? So if I pick another path that connects those two, then the integral along this path and then back along this path is going to be 0, which means the integral along each path is going to be equal to each other. So that tells me that the function is well defined, and the only thing left to prove is show that f prime of z equals f of z. And this is the part that I'm sort of going to skip, because these get pretty involved, these limit arguments. you've seen this proof actually in calculus, right? When you prove the fundamental theorem of calculus, you define the antiderivative as a derivative, and you do an integral, and you show that the derivative of the integral is equal to the function. This is a little bit tricky. It involves a lot of epsilons and deltas, so I don't want to go into that in too much detail. I will note something here. And this will occur over and over again in the proofs. Right? Whenever I say limit argument, right? What am I talking about? I want to show that two things are equal to each other. In this case, I want to show that two functions are equal to each other. So if I want to show this is true, how do I go about doing that? Right, so to show two functions are equal, you have to show f of z minus d of z. F of z equals g of z for all z in whatever your domain is. So how do you do that? Well, you actually show that, right? Show that the difference is equal to 0. Okay, but really we don't want to show that because that's pretty complicated. Since everything's complex, what we can do is to show that the modulus of the difference is equal to 0. So that takes us down from the complex plane. Now we're just dealing with real numbers because we have that. Or one way that we think about modulus in the plane is that it's actually a distance. It's the distance between the two things. Remember when we're defining circles, right? It's the distance between two things. So I can think of absolute the modulus of f of z minus g of z as the distance from f to z is, and I don't want to have it be distance, is 0. There we go, that makes more sense. But what I'm actually going to show is the following statement. And that's actually the argument that you show. For every epsilon greater than 0 and for every z in the domain, f of z minus g of z is less than epsilon. And in words, what this is saying is I want to show that in words, what this is showing is that the distance between these 2 points is actually less than any positive number, right? And distance has to be positive or 0. And so if it's less than every positive number, the distance has to be 0. So once you show that, you can show that f of z is equal to g of z. So whenever I say there's a continuity argument or a limit argument, that means somewhere in there we have to prove this thing. And proving that thing gets involved in a lot of inequalities, which I love. Personally, I love inequalities because they show you a lot of things about functions. But it's easy to get bogged down into the technicalities of proving that. And so rather than going through those details all the time, I'm going to just say there's a continuity argument or there's a limit argument. It means this, and you can see it in the video on the proofs. So here in this lecture, we just want to get through what they mean, and then the details will be somewhere else. So Kochie-Grassat theorem. is saying if we have a closed smooth path and f is analytic on and inside gamma, and so on and inside gamma means I've got a path, gamma, closed smooth path. And that means that there's some open set containing the path and f of z is analytic everywhere on the path and in it. Then the integral around gamma of f of z dz is equal to 0. This is a little bit hard. This is entirely a limit argument, and it's a particularly, I think it's a particularly messy one. And this is the one, let's see. If you have the book, I'll hold this up. I know you won't be able to see it, but if you have the book at the very bottom there, it says, if you don't want to see the proof of this, just skip it, because it's a long and technical proof. And essentially it boils down to taking our curve gamma and building inside a whole bunch of little squares and saying, if I integrate around the little squares, I can make those integrals as small as I want around each of those little squares, right? The little squares will have width epsilon. So I can make those as small as I want. And so I can get that the integral around the whole curve is the integral around these really, if you just add up the integrals around all the little curves that you have, the squares, that'll end up being the integral around the curve. But the integral around all the squares I can make as small as I want. So I can make the integral around the whole curve to be less than any positive number, which means that the integral has to be 0. So that's a particularly nasty one. In fact, it's so nasty to prove that the book sort of says, skip the proof because it's pretty nasty. But I'll put the proof there. I mean, there's actually some really interesting things in there. So we'll put the proof there in the proof video. Okay, so, but you can see that this conclusion ties to this conclusion. They're very similar. The hypotheses are different. Here we just needed that f of z is continuous. Here we have that it's f of z is analytic on and inside gamma. So here's where the domains come in and become important. So suppose we have a simply connected domain. That's D. And the interior of that is by simply connected D. F of z is analytic on D. And remember that D is open, so D doesn't actually include this boundary that I drew. I suppose technically I should have made it a dotted boundary. And gamma is a smooth curve, closed smooth path inside of D. Well, f of z is analytic on D, so that means that gamma is a smooth closed path. That means this integral is equal to 0. Okay, so, and that's just an application of the previous theorem. And note, what that is that's condition 3 of the Tfa theorem, right? So this is saying that if I have a closed smooth path in D, then integral around f of z dz equals 0. If this is true, then I get the antiderivative. And so this theorem is saying basically, if you're on a simply connected domain and f is analytic, then the third condition of that holds. So, oh boy, if my pen starts breaking, that would be sad. So, there is an antiderivative, and these integrals are path independent. So what we've got then is then now we've connected these integrals around paths with the equivalent statements up above. So now we have antiderivatives as long as we're in a simply connected domain and we have an analytic function. This is important because when you think about things like e to the z, polynomials, sine of z, cosine z, hyperbolic functions, all of those things are analytic on the entire plane, right? And that's a simply connected domain. So functions like e to the z, polynomials, f of z, sine of z, all these things have antiderivatives, the usual antiderivatives that you see from calculus. What about multiply connected domains? So this has got a ton of words in it, which is kind of horrifying, but it's actually pretty straightforward. Gamma is, and you probably saw this in vector calculus. If gamma is some big, positively oriented, simple, closed smooth path, so here's gamma, and gamma k oriented this way, so you're going around it with the interior on your left. Gamma k are negatively oriented simple closed curves so that the trace of gamma k is inside the interior of gamma. So I'll draw 3 of them. Gamma 1, gamma 2, gamma 3. They're negatively oriented, which means I'm going around them this way with my interior on my right. And this statement here is kind of long. It's just saying if you take 2 different curves, the traces don't intersect, so gamma 1 and gamma 2 don't intersect, and the interiors don't intersect. So these are sort of disjoint curves that separate things out. And f of z is analytic on this path, this path, this path, this path, and everywhere in between, right? So in the interior of gamma and on intersection, the union of the exteriors. So that's this region out here. And what it's saying is that the integral around this curve is equal to the sum of the integrals, plus the sum of the integrals around these curves equals 0. Right? And you've seen how to prove this. Basically, you say, okay, let's take a path gamma, we'll take a path sigma, which is, we'll just pick a point to be the start and end of gamma. And we'll pick a point here, and we'll call this Z1, and you take gamma to Z1, and then you take a path here, which we'll call sigma 1. No, this whole thing is, yeah, sigma 1. Right? You take sigma 1 down here, you go around the path, and then you take sigma 1 back up to Z1, but going the other way. And then you go around further, get to a point here, which we'll call Z2, create a path sigma 2 that'll take you to gamma 2, follow gamma 2, come back. Same thing here, come back and end up there. So what you've done is now you've got a closed loop where the interior is entirely on the left side. So it's positively oriented. And the function is analytic everywhere on that. So the integral around that closed loop is 0, but then you can break it into 3 different parts. The integral around gamma the integral around each of these things, and then the integrals along the sigma 1 up and the sigma 1 back. But those two, the up and back parts, those will cancel out. And so the integral is 0. We have to be a little bit careful about the sigma 1s because we don't want to have a huge number of intersections. So we actually need to have two paths that are very close to each other, and then we can make that small. So, and then we have something called the principle of the deformation of paths, which just tells us that if I have one path going around another path, and this is gamma 1 and this is gamma 2, then integral around gamma 1 of f of z dz equals integral around gamma of 2 of f of z dz. And so what that means in part is so suppose I want to find this integral of gamma of 1 over 1 plus z squared. This function is defined, and we'll put I here and minus I here, and we'll make gamma some big thing like that. And that's a function that's defined except at z equals I and z equals minus I. It's analytic everywhere except those 2 points. So here's my gamma. What I can do is I can actually find two small circles, call them sigma 1 and sigma 2, that surround I and minus I. Then the integral around gamma of 1 over 1 plus z squared dz will be the integral around sigma 1 of 1 over 1 plus z squared dz plus the integral around sigma 2 of 1 over 1 plus z squared dz. The nice thing about that is if I make this into a circle, right? R1 e to the I should call it t because I've been using t as my parameters, plus I. So a small circle of radius 1 centered at I. That's easy to integrate because now I've actually got a nice parameterization, and so I can actually do this integral as opposed to having some big random curve gamma. Okay, so these proofs give us some very nice results about functions. One is the Kochie integral formula. So if I have a positively oriented simple closed smooth path and f of z is analytic on the path and in the interior, and z0 is anywhere in the interior. So what's the picture? Here's some gamma, positively oriented, so we're going this way around the path. Simple, doesn't intersect itself. Closed, starts and ends at the same point. Smooth, it's got a derivative. Path, it's a function from the real line into the complex plane. F of z is analytic on this, some subset a little bit bigger than that. And z0 is any point in the interior. Then we actually get a expression for this. I can integrate this thing which I'll call g of z, and I can get the value of the function there. And that's actually a really nice thing to do because it tells you what the function is. Integrating this is a little bit messy because you do get into another, this actually becomes a very messy thing. If I take this integral right, which is f of z minus f of z0, and split it into two integrals. Right? So what have I got there? This integral, I don't know what it is, but it's the integral that I'm interested in, that's this part. Minus the integral of this thing. But this, that's just a constant, it's f of z0. So this is f of z0 times the integral around gamma of 1 over z minus z0 dz. But this integral here, what we just learned is I can take a little tiny circle around that and do an integral around that, and that tells me what the integral around the whole path is going to be. And we've done that, right? We've actually, one of the homework problems earlier is integrate this around a circle centered at z0. And what do you get? This integral here, if you integrate it around a circle centered at z0, is just going to be 2 pi I. So the goal is, here's the function, the integral that I want, and what I want is I want it to be equal to this, which means I want this to be 0. So if I can show that this thing is 0, then this has to be equal to this, and then that gives me that I can solve for f of z0, and the function z0 is actually, at z0 is actually just an integral. This thing here, right, that's awful close to being f prime of z0, right? You take the limit as z goes to z0, and that's in fact f prime of z0. So getting this to be 0 involves another continuity argument. Right? But you're basically sort of integrating the derivative there around a closed path, so you should get 0 because it should be because f is an analytic function. And you can extend the Kochie integral formula. This is actually pretty simple. We know f of z is the 1 over 2 pi I, the integral around gamma of f of, well, f of z is, we'll use w here. So that's the Kochie integral formula from there. W is what's called a dummy variable. You're integrating with respect to w, so when you do the integration, the w's go away, right? You replace the w's with the limits of your integral. And so when you do the integration, the w's would go away and you're just left with z. Z is the actual variable, right? Okay, so what's f prime of z? So this is just a constant, so I can ignore that. There's a, well, I can't ignore it, but I can bring it outside of the derivative. And then we get 1 over 2 pi I times the derivative of this integral, and the z appears there. That's the thing that we're taking the derivative with respect with. So since this integral is with respect to w, but the derivative is with respect to z, I can interchange the integral and the derivative. And that's a thing from Calc 3. although I will include some details about why you can do that. So this is going to end up being the integral around gamma, 1 over 2 pi I, I always forget the constants out front, of d by dz of f of w minus z to the minus 1 dw. But we're differentiating with respect to z, so this part is just a constant. Then I have to do a little chain rule action here on the w minus z, so this becomes 1 over 2 pi I integral of around gamma of f of w minus 1 w minus z to the minus 2 times minus 1 times dw. Right? Because when you differentiate this, the minus 1 comes out down out front. You get a minus 2 in the exponent, but when you're differentiating, you have to differentiate the thing inside, and that's going to give you another minus sign. So you get a minus sign here and a minus sign here. They cancel out. And I just get 1 over 2 pi I integral around gamma of f of w minus z to the minus 2. And then you can differentiate again, right? And if you differentiate again, you're going to pull down a 2. So the second derivative will have a 2 out front. If you differentiate that again, you're going to pull out a 3. So the third derivative will have a 3 times 2. And you can see how the factorial is going to pile up out front. So the nth derivative can be estimated by doing this integral. So why is this a really useful, important theorem? Well, because we have the ML theorem, right? I can find bounds on these numbers because I can put a bound on the integral, and the bound on the integral is less than or equal to the maximum of the integrand times the length of the path. What this theorem tells me is that I can actually make the paths really small, right? If I want to find the integral around this path, I can pick really small paths around here and just do the integral there. So if I'm trying to estimate how big f of z can be, I can look at this thing and estimate this integral. I can make the path really, really small. The problem is that the closer I get to z0, the smaller I make the path, the bigger that gets, right? Because you're coming very, very close to dividing by 0. So you're going to have a little bit of a problem there as the path gets smaller, right? The path length gets smaller, but the modulus gets bigger. And often when you're trying to estimate that, you're trying to see if you can make them both small so you can get some kind of an estimate. And often that happens. So what we actually get here is that the derivatives are, from the Kochie integral formula, the derivatives are analytic because you can express them in terms of this integral. And this has a really nice thing for if you're dealing with real and imaginary parts of an analytic function, right? And these are called harmonic functions, which you'll see often in physics. So the two parts are harmonic. And so if we actually have harmonic functions, what we get from knowing that the derivative is always analytic, these things have continuous partial derivatives of all orders, right? These things have lots and lots of derivatives, right? You never come across a bizarre singularity somewhere in the derivative, which you can do in other problems, other types of functions. So harmonic functions are really nice because the real and imaginary parts of analytic functions. Harmonic functions show up a lot in physics and other applications. A lot of the properties of harmonic functions can be established by looking at analytic functions and establishing properties of that, because harmonic functions are real and imaginary parts of an analytic function. So Morera's theorem, this is another tricky one to prove, but it says if D is a domain and f of z is continuous, and for all closed smooth paths gamma with trace gamma we have this, then f of z is analytic. So from the Tfa theorem, Oh, Theorem. That's terrible. What was it? One of the conditions was if f is continuous and integral around gamma equals 0, right? If we have this condition, right, that's connected to having an antiderivative. If that's true, then you have an antiderivative. But having an antiderivative means that you're the derivative of a function. That doesn't necessarily mean that it's actually analytic. But we can show that this actually implies not just that f has an antiderivative, but that little f itself has to be analytic. And this is another limit argument. And so it's kind of connected to the Tfa theorem. Okay, but that's a little bit, I'm kind of following the sequence that's in the book. Morera's theorem seems a little bit of out of place because we're still going to be working with the Kochie integral formula. So what we've got now from the Kochie integral formula is a way to say that if I have a function and I want to know what its values are, I can build up integrals to express those values. The important thing about having functions expressed as integrals is that we have the ML theorem, which tells me that I can find estimates for how big something can be, right? If I've got an integral along a path, the modulus of the integral has to be less than or equal to how big the function can get times the length of the path. And if the function, if I'm defining a function in terms of that integral, that gives me a way to estimate how big something can be. And this is Kochie's inequality, which is just formalizing that a little bit. If I take a circle in particular as my path, and f is the analytic on that, and there exists an m greater than 0 for all z and trace of gamma f of 0 equals m. So this is a lot of symbols that just means f is bounded on gamma. Well, fn of z0 has to be less than or equal to this, because the length of my path is 2 pi r, m is my maximum, and if you just estimate this integral, right, this part has to be less than m over r to the n plus 1, and the length of the path is 2 pi r, so you end up with m over r to the n and then n factorial there. So what this does is it actually tells me that I've got a bound on how big my derivatives can be. And so in particular, right, entire, and just remember that entire means analytic on the plane. So analytic everywhere. I can make r as big as I want, right? I can make r go to infinity. So what does that tell me? That tells me that the derivatives, the nth derivatives of an entire function at a point have to get smaller and smaller and smaller in modulus, because they have to be less than or equal to r to the n, unless m is getting bigger with r to the n as well. So this ties together, right, the maximum that you can be on a curve with how big the curve is, right? As the curve gets bigger and bigger and bigger, if I don't want my derivatives to all drop down to 0, the maximum on that circle has to get bigger and bigger and bigger and bigger. Right, so it tells me something about how fast my functions have to grow. The maximum has to grow something like r to the n. And that sort of leads you into Liouville's theorem, which says that if a function is entire and it's bounded, right? So defined in the entire analytic in the entire complex plane, bounded, oops, sorry about that. If it's bounded by m on a plane, then in fact, the function has to be constant, right? And that's a really kind of weird thing, right? If you have a bounded function, it has to be constant if it's defined in the entire plane. And essentially the argument is that from Kochie's formula, we have that the derivative of f at any point is equal to 1 over 2 pi I integral around any gamma that goes around z0, f of w over w minus z0 squared dw. But this part is bounded by m. If I take gamma to be a circle, right, and just make it really, really big, the thing in the bottom is now, if I plug in gamma, it's gonna, the z0s will cancel out and then just be r e to the it. So if this is bounded and I make r really big, then this whole thing is gonna go to 0. Which means that f prime of z0, the derivative, has to be less than or equal to every positive number. If something's less than or equal to every positive number, it has to be 0. So that means that if f of z is entire and bounded, then it has, its derivative is 0, and if its derivative is 0, it's constant. So what does that tell you about a function like what about sine z plus 2? If you think about the real line, oh, that's a little annoying. If I can do that. Nope. Oh, sad. Okay, what about sine z plus 2? If you think about the real line, what this looks like is 1 to 3, and sine does that. Right, so sine of z plus 2, well, sine of x plus 2 looks like that. And it certainly looks like a function that is bounded and defined everywhere, certainly on the real line. But you can't have that. You can't have this kind of behavior on the complex plane. You can't have something that's bounded everywhere, right? This is always less than 3. Bounded everywhere and defined everywhere and analytic everywhere. So what does it tell you about sine z plus 2? Well, we know that's entire because it's got a derivative. So this has to go to infinity somewhere, right? And in fact, if you look at sine along the imaginary axis, that actually goes up to, it's actually an exponential function. It'll go up to infinity on one side and minus infinity on the other side. So sine I of z is actually, I think, I times sine of IB, where B is a real number, is actually I times hyperbolic sine of B. And so along the imaginary axis, sine is an unbounded function. So a lot of the functions that you think of bounded, in real analysis, they end up being unbounded somewhere. In complex analysis, there has to be some path you can take out to infinity that'll make the function unbounded. And finally, we've got two things left. Fundamental theorem of algebra. If P of z is a polynomial, then there exists some z0 so that P of z equals 0. And so building up a lot of machinery gets us to the point where we can say, well, suppose we have a polynomial that doesn't have any roots. It can't be factored. Well, that means that 1 over the polynomial is defined everywhere because the polynomial is never 0, so I'm never dividing by 0, and it's analytic on the plane. But what we also know is that if I take some really big radius r and we look everywhere outside here, you know that the polynomial well, normal polynomial is going to be z to the n times, let's see, an plus an minus 1 over z plus an minus 2 over z squared plus dot, 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 all the way down to a0, 1 over z to the n. So if you think about a polynomial, factor out the highest power, right? And you get something like that. And, you know, in calculus, when you're doing all these limits about, you know, limits is going to infinity, you factor out of rational functions, you factor out the highest powers in the top and the bottom, cancel them out, and then all these things go to 0. So limit of 1 over p of z, the modulus of that, is actually equal to 1 over the modulus of z to the n times the modulus of 1 over all this stuff. So it's going to be less than or equal to 1 over r to the n, because this is the only term that's important when you get really, really large. And you can ignore this part. So outside of the circle, 1 over p to the z is bounded. Inside of the circle, well, it's defined everywhere, so there's a biggest value inside of the circle. So I've got a bound for the inside, I've got a bound for the outside. So 1 over p of z is defined, analytic, and bounded. And that tells me that 1 over p of z is constant, which means p of z is constant, right? So if you do not have a 0, then your polynomial has to be a constant. Which means if you have a non-constant polynomial, then you've got to have a 0 somewhere, so you can factor. So that's very nice. And then finally, we get the maximum modulus principle, which tells us about if I have a ball of radius epsilon centered at z0. So there's z0. There's my radius epsilon. And I have, for all z inside of this ball, the modulus of f of z is less than or equal to f of z0. And remember that z0 is the center, right? So we're saying that the modulus of the center is bigger than the modulus of f anywhere else in the circle. So the modulus has a maximum at the center. So what that tells us is, in fact, is that for some c and for all z inside there, f of z equals a constant. And in fact, f of z equals f of z0 everywhere in there. It's very similar, actually, to the fundamental theorem, to Liouville's theorem. Liouville's theorem is on the entire plane. This is just on a little disk. But it tells us that you're actually going to be a constant there. And this is going to be another limit argument, which is annoying. So we'll see that proof of that. But what that also tells us is that if D is a domain and f of z is non-constant analytic on D, then there's no maximum on D. So if there was a maximum, so if I have some big region D, and this could be multiply connected, there could be holes or whatever in D. But suppose the maximum was here, and I pick some other point Z1 here. Well, I can put little circles. I can pick a bunch of points that go from 0, 0 to Z, put a bunch of little circles around them that overlap a little bit. Analytic with a maximum means you're constant inside the disk. So we must be constant inside of the first disk, but that overlaps with the second disk. So can the second disk be, so the second disk actually has to be constant as well because of the same thing. There'll be a maximum inside there, and you can just chain them together and end up at the bottom. So it tells us that the modulus never has a maximum, which actually makes a lot of sense when you think about some of the properties we have. And if you think about this in terms of heat flow, right? So heat flow will have, the level curves of heat flow is a harmonic function. So if I have, say, some kind of an object, and suppose I keep one side at 100 degrees and the other side at 50 degrees, and this side at, I don't know, varying between 150 degrees, say 75 degrees plus 25 degrees sine x. So the temperature here varies as you go from left to right. And we'll say this is, I don't know, just insulated so you don't lose any heat that way. What kind of a heat flow are we having? We're gonna have heat flowing like this and like that. It'll be a complicated kind of a heat flow. But you know something about harmonic functions, right? If the heat flow is following a harmonic function, so there's no sources of heat inside there and no places where it's draining out except at the sides, if it just flows across there, there's no maximum or minimum inside that sheet. The heat has to flow, right? And it can't pile up in any place. And so this has, this has applications for harmonic functions. Harmonic functions can have maximum minimums, which means heat flow can't have maximum minimums. The only way you can actually have a maximum minimum, a hot spot or a cold spot inside there is if you have some kind of way to drain off the heat somewhere. And the only way you can drain off the heat is by having it go out one of the sides. So complex functions, the maximum, the modulus has no maximum, which has some implications for some applications. So basically what we have then is we have this sequence of theorems that says, well, let's start by thinking about the interaction between paths and analytic functions. And what do we know about the integrals? And where we actually end up is that if you're analytic, then the integral around a closed path has to be 0, which means you can reduce your integrals to just small integrals around places where the function has a problem, right? So you look for places in the domain where you have a singularity of some sort, and you say, okay, well, any integral I can have, I can replace it with this integral around this particular, it's an integral around around a circle around that particular problem. So that's one thing that you can do is you can isolate the problems of a function and say, well, outside of that, I don't have to worry about that. I just have to deal with the integrals inside. The other thing is Kochie's integral formula tells me that the function, the value of the function is related to a particular integral. And that's a really powerful tool because it allows you to estimate how big functions can be. Having that tool, right, because we can estimate how big integrals can be, so that means we can estimate how big functions can be. Having that tool allows us to do things like Liouville's theorem and the fundamental theorem of calculus. Okay, so that's sort of the big picture of where we're going. It's a whole bunch of theorems that are sort of related to each other, so I just want to go through them together. There'll be a video that will do the proofs. There won't be any notes required for that video because that would be, I have no idea how long this video is going to be, but you should definitely watch it. And on Thursday, what we'll do is we will, you can, bring this list of theorems and we'll sort of have some problems that'll start connecting them together so you can start thinking about them in a coherent way. Okay, so for those of you who stayed through all this, thank you for doing that. Are there any questions before we sign off? Nope, okay. Great. Well, I will stop the recording. Pause, stop recording.